Dear students, last time we have discussed that how Italian mathematician Raphael Pumbelli solved the carton puzzle by considering square root of -1 to be a valid number. Later on, Swiss mathematician Euler gave it the name imaginary number and symbol I, which is known as iota. Students, these imaginary numbers obey mostly the rules of algebra like that of the real numbers. Now, I would like to discuss one rule that these imaginary number obey like that of the real number. So suppose we have any two real number with their product inside the square root. Suppose we have two numbers like 3 into 5. So the product of any two real numbers inside the square root can be broken into separate parts. This can be written as square root 3 into square root of 5. Students, same rule can also be applied to these imaginary numbers. Suppose we have any imaginary number -9. So this number can also be broken into separate parts. This can be written as 9 into -1, which is equal to square root of 9 into square root of -1, which is equal to 3 iota. Because we know that square root of -1 is iota and square root of 9 is 3. So let us consider one more example. Suppose we have a number square root of -3. This can be written as 3 into -1, which is equal to square root 3 into square root of -1, which is equal to square root 3 iota. So suppose for any general case, that is, we can generalize now this for any real number r. Suppose we have any real number r, then the negative square root of any real number r can be written as iota square root of r. But here the condition is that r must be greater than or equal to 0. This r should not be negative. Ignoring the sign, this r must be positive. This sign is negative. So there are only two key properties that distinguish these imaginary numbers from real number. They have mostly common properties, but the two properties that distinguish these imaginary number from the real numbers are: the first property is that I square is equal to -1, or we can say that square root of -1 square is equal to -1. And students, the second property is that suppose we have any real number r, then minus of -r is not equal to I times square root of -r. Because if we allow this to happen, then we will get a very nonsense results. So I will explain you with one example. Now we know that 3 is equal to, I am taking the example of 3 because I have done previously. We can write 3 as square root of 9. Now students, this square root of 9 can be written as square root of -9, and this can be written as square root of -1 into -9, or this can be written as square root of -1 into square root of -9. Now we have previously proved that square root of -9 is 3 iota and square root of iota is, square root of -1 is iota. So this can be written as iota into 3 iota. So this is 3 iota square, or which is equal to -3, because iota square is -3. So we have proved that 3 is equal to -3, which is not possible. Why we have proved? Because we have assumed that square root of -r is equal to iota times square root r. Here we have assumed it. So if when we assume this identity to hold, in actually it do not hold, but if we assume that this is equal to this, then we will get a nonsense result: 3 is equal to -3, because in this part we have assumed that we can write this as equal to. So this is a second property which distinguishes these imaginary numbers from the real numbers. So student, the next question for the mathematician is that if these imaginary number exist, because we have previously proved that if this imaginary number exists, then we can find a square root of any negative number. Now the next question that mathematician has to think is that if these imaginary number exist, then where do they exist in the number system? So to answer this question, first of all, let us consider the algebra of I. Now students, we know that if we raise real number to higher and higher power, they will get bigger. For example, 2 to the power 0 is 1, 2 to the power 2 is 4, 2 to the power 3 is 8, 2 to the power 4 is 16, 5 is 32, 6, 64. So number is getting bigger and bigger as we raise it to higher power. Now see the for imaginary numbers. Suppose we have I. So I to the power 0 is 1, I to the power 1 is I to the power 2 is minus 1, that we have previously said. Now I to the power 3 can be written as I to the power 2 into I. So which is equal to minus I, because I square is minus 1 and minus 1 into I is minus I. So I to the power 4 is I square into I square, which is equal to minus 1 into minus 1, which is equal to 1. Because I4 can be broken by the law of indices as I square into I square, and from our this result we will get 1. Now let's go for more higher powers. I to the power 5 is equal to I to the power 4 into I, which can be written as 1 into I, which is equal to I. Now I to the power 6 is equal to I square into I4. Now this is equal to 1 into I square. Now I square is minus 1, so this is minus 1. Similarly, I to the power 7, you can prove that similarly I to the power 7 is minus I, and I to the power 8 is plus 1. So student, we see from the algebra of I, or from the algebra of imaginary numbers, that these numbers do not get bigger as we raise it to higher and higher power, in contradiction to that of the real numbers. We can see that after every fourth power, the value of I repeats. For example, if we have I1, I to the power 1, its value is same as I to the power 5. So students, before I will show you where these numbers exist in the number system, you have to keep this property, cyclic property of this imaginary number into your mind. Now let's return back to our original problem. Our problem is to find a number on a number line that multiply by itself will yield a negative. Or we can say that if we have a number square root of minus 1, then its square will give minus 1. Now on a real number line, if we see our real number line, now Gauss visualize this problem in this way. Gauss was the first person who give the position to this imaginary number in the number system. So please see very carefully how Gauss give their position. Now this is a real number line, and suppose this is 0. So on the right hand side of the 0 we have all positive real number, and on the left hand side of this 0 we have all negative real numbers. Now students, if we multiply any positive real number with minus 1, we will get same real number with negative sign. Now if we multiply any negative real number with minus 1, we will get same real number with positive sign. Now if we multiply any positive real number with plus 1, we will get the same positive real number. And if we multiply any negative real number with plus 1, we will get the same negative real number. So student, this means that multiplication with plus 1 gives us rotation of 0 degree. You can see, because if minus r remains minus r, it means you have a rotation of 0 degree. And if plus r remains plus r, when you multiply with plus 1, it means you have a rotation of 0 degree rotation. Here you will also have 0 degree rotation. Now if we multiply any real number with minus 1, we will get the same number with sign reversed. It means this number will come to this side and this number will go to this side. It means we will have a rotation of 180 degree. So this will give rotation of 180 degree. So student, here the conclusion is that multiplication of any real number, whether positive or negative, with minus 1, rotate it by 180 degree. Now suppose if we want a number that gives a rotation of 90 degree, then we have no such a number on this real number line. because on this real number line no number will give you a rotation of 90 degree. Now this rotation of 90 degree is what was given by imaginary numbers. Now see, because we have shown from the cyclic property of this imaginary number that I square is equal to 1. Sorry, I square is equal to minus 1. This means that if we multiply I twice, we will get minus 1, or we will get a rotation of 180 degree. It means if we multiply I once, we will get rotation of 90 degree. So this means multiplication by I correspond to 190 degree rotation. So I think you are getting my point. Now you see, because I square is equal to minus 1 and minus 1 is a rotation of 180 degree. It means I into I is minus 1. You can break I square as I into I. It means if you multiply I twice, you will get a rotation of 180 degree, and I have shown that what is the significance of minus 1. Minus 1 geometrically means rotation of 180 degree. If you multiply any number with minus 1, its geometrically significance I have shown that is rotation of 180 degree. It means what will be the physical significance if you multiply any real number once with I? It means it will rotate that number by 90 degree. So students, Gauss use this idea and place these imaginary numbers at right angle to the real number system. So this position that these numbers will exist at a perpendicular dimension to this real number line was given by Gauss, and by using this idea that multiplication with I will correspond to a 190 degree rotation, and when you multiply with I twice, you will get a rotation of 180 degree. So you can visualize this as, suppose this is plus 1. Now if I multiply this real number with I, so it will give me a rotation of 90 degree. Multiplication once with I, it will give me a 90 degree rotation. Now if I multiply this real number with I again, it will further give me 90 degree rotation, and I will reach minus 1. So student, this is the deeper meaning behind these imaginary numbers. These imaginary numbers are as real numbers, because as a real number when we multiply with the real number with minus 1, it gives us a rotation of 180 degree. Similarly, if we multiply any real number with this imaginary number, it will give us a rotation of 90 degree. So in this way, we can say that our number system is two-dimensional. So two-dimensional. If our number system is two-dimensional, then we place real number along this axis, on horizontal axis, and on vertical axis we place our imaginary number. And when these two number lines will meet, they will form a plane. They will form a plane as is formed in xy plane. As we intersect our x and y axis, we will get xy plane. Similarly, if we fuse our real axis and imaginary axis, we will get a complex plane, and this plane is called complex plane. And any number in this complex plane is called complex number. Suppose this side we have real numbers 1, 2, 3, 4. In this side we have negative real numbers -1, -2, -3, -4. This side we have positive imaginary number I, 2i, 3i, -i, -2i, -3i. So suppose this is any point. So this is point 2 plus 2i. So this point on this complex plane, this number is called a complex number. Basically, there is nothing complex about this. These are given the name complex number because it is a combination of two number system. One is a real number system, another is imaginary number system. Otherwise, these number are very simple. These complex number also follow the same rule of algebra like real numbers. So students, my main motive to introduce to this mathematical background before studying your physics course is that because these imaginary numbers are used in many branches of physics. You cannot have a proper deep understanding of the concept of physics if you do not know the origin of this complex number system. So I think in this video I have done enough mathematics and concepts for you that you know that why these imaginary numbers originate and what is the deeper meaning behind them. So now, before concluding my lecture, I would like to tell you some of the application of these complex numbers in our science and engineering. Now students, these complex numbers are used to describe our AC circuits, because in our AC circuits we have different components. You will study, or you have studied, that in AC circuit we have different components. We have resistance, we have inductor, we have capacitor, and these different components behave differently or react differently to the current, due to which there is a certain phase relationship between current and voltage, and these complex number give us a very compact way of writing that phase differences. So that's why the mathematical background of this complex number is very necessary for you. Moreover, when you will study the motion of the objects in a complex plane, you require this complex number. Anything that you have to measure in terms of waves, you require this complex number there, because in wave you have a certain phase relationship, and that phase relationship you can only describe by using these real and imaginary numbers, and that is complex numbers. Moreover students, the most fundamental theory of physics, that is quantum mechanics, the equation that describes quantum mechanics is known as Schrödinger wave equation. And students, in that Schrödinger wave equation you have a complex number, or you have a imaginary number I in it. So their number are such important to study the physics. Students, now then these numbers are not only used in physics, they are also very useful in engineering. For example, civil engineers use these complex number to do their calculation when they have to study the vibration in the bridges. Moreover, your in electricity, in communication system, your engineers use this number to study the electromagnetic waves. Moreover, in biology, these complex numbers are very used. For example, biology, in now the current researches in biology, the people are studying brain waves. Biologists say that we have a brain wave. Inside the brain we have a brain waves. So for analysis of that brain waves, these complex numbers are used. So students, my main motive behind to go into the depth of the mathematics before starting my course is that you will not feel that these imaginary numbers are very, very extraordinary, that we do not like it. So I have to give you a a very comprehensive introduction about these complex numbers. So students, in my next video I will come with some other physical quantity, other mathematical quantity that is very much used in your physics and engineering course. So it is my humble request to you to all that please like and subscribe my channel, so that maximum students can benefit from this channel. So thank you, and meet you again.